This problem asks us to take the derivative of a fairly complicated equation using implicit differentiation. One quick note: the derivative of the inverse tangent function is 1 over 1 plus x squared in general. And we'll put that to work, obviously, as we get into this problem. One other thing to note is that we have two functions multiplied by each other in the original problem, so we'll have to use the product rule as we get further along. Taking the derivative of the first term gives us 1 over 1 plus y squared. And then we need to continue with the chain rule, thinking of y as being a standalone function. And it's dy dx. The derivative of x with respect to x is just 1. Now it's time to do the product rule with this next term. We start out taking the derivative of the first function, which is dy dx, and then multiply it by leaving that second function alone, natural log of x minus 1. Product rule goes on to say we add, and now we leave the first function alone as a y, and multiply it by the derivative of the second function, which is 1 over x minus 1. The derivative of the right-hand side of 2 just becomes 0. Moving on, since we're trying to solve for dy dx, we want to get all the terms that have dy dx in it on the left side, and move all the other terms to the right side. On the left-hand side, we stay with 1 over 1 plus y squared times dy dx. The 1 gets moved to the right-hand side. The dy dx times natural log of x minus 1 stays. And on the right-hand side, we have negative 1 minus y times 1 over x minus 1. We want to narrow the left-hand side down to having just one dy dx in it. So we'll do that by factoring. If we factor out a dy dx from these two terms, inside the parentheses we'll have 1 over 1 plus y squared plus the natural log of x minus 1. On the right-hand side, we'll do a bit of algebra simplification, multiplying the y times the 1 over x minus 1 to create a single fraction. We're now ready to solve for dy dx. All we have to do is divide both sides of the equation by the large expression that had been in parentheses on the left-hand side. That leads us to our final answer of dy dx equals this expression on the right-hand side.